We'll start the plenary conference with the topic Data Mining in Predictive Maintenance Overview and Applications, which is going to be presented by Mr. Sebastián Ventura Soto.
Thank you, Noela. I am the session chair of the plenary conference. First of all, I will present a short biography of Professor Sebastián Ventura Soto. Sebastián Ventura Soto currently serves as a full professor in computing science and artificial intelligence at the University of Cordoba, where he also heads the Knowledge Discovery and Intelligent Systems Research Laboratory. He has published more than 200 papers in journals and scientific conferences, and he has edited 3 books and several special issues in international journals. He has also been engaged in 12 research projects, being the coordinator of 4 of them, supported by the Spanish and Andalusian governments and the European Union. His main research interests are in the field of soft computing, machine learning, data mining, and their application. Okay.
First of all, thank you for your introduction, for your gentle invitation to this conference. Thank you to the rest of the organization for thinking of me to organize the conference. I have prepared a conference related to the last research project we are working in, that is about predictive maintenance, because I thought it fits with the main topic of the conference. So I will try to be brief. And before starting the presentation, I'm going to give a short introduction to my research group. My research group is located in Cordoba. You know, Cordoba is in the middle of Andalusia, in the south of Spain. We are 10 PhD researchers and several PhD students, and all of us works on machine learning, data mining, data science in general, and its application with 2 different topics. We started working on the application of data mining to education, but in the last year we have moved our research to the clinical data mining topic and the industrial topics, as we can see in the slide of the presentation I'm going to do. Okay, so once I have done this short presentation of the group, the link to the look is should be in the presentation. I forgot to put it. No problem. I'm going to start to the presentation now. Okay. I hope you can see it well.
Yes.
I'm going to stop the video in order to allow a bigger bandwidth. Okay. This presentation is about predictive maintenance and its relationship with data science. I have organized the presentation in 4 main parts. The first is an introduction to the topic. The second is about generalities about data science and predictive maintenance. And the third part is about several examples of successful cases of application of predictive maintenance, and I will finish presenting one project we are developing currently that is called ManPredict, related with the predictive maintenance of military trucks. Currently, the industry is going through what experts call the fourth industrial revolution, also called the Industry 4.0. This term refers to the digital transformation of manufacturing, production, and related industry and value-creating processes. The main feature of Industry 4.0 as an evolution of Industry 3.0 is the autonomous work of machines without the intervention of humans. This fact is a consequence of the appearance of civil physical systems, systems that are comprised of smart machines, storage systems, and production facilities capable of autonomously exchanging information, triggering action, and controlling each other independently. This exchange of information is done by the industrial Internet of Things, in which thousands of sensors work in real time and transfer the data to a local server or a cloud server. These figures show all the new technologies that are related to Industry 4.0. Many of the elements involved in this system are autonomous agents that regulate themselves according to the information they receive from different sensors. This sensor can also transfer the data to cloud storage systems. Simulation models can help to understand the operation of various elements, and different subsystems use this information to perform some control action when necessary. As can be assumed, the security of the system, both the data transfer and the access of the device, is really important, which is why the figures show the elements of field of cybersecurity too. On the other hand, the application of big data analytics over the data produce models that help to verify the health of the simulation models. These models can also provide useful knowledge, as we explain later. Other technology of interest will be, for example, the augmented reality, which allows us to improve some of the simulation systems. In the Industry 4 context, data analysis is carried out through the development of predictive models that help the organization to anticipate some irregularities in the process or systems, so that action can be taken well in advance. This way of carrying out machine maintenance is called predictive maintenance, and it will be the main topic of this speech. Industrial maintenance, also known as plant maintenance, is the application of reliability best practice to increase equipment uptime in a manufacturing environment. This concept importance is evident as the capacity and quality of an organized production depend on the availability and reliability of the equipment. The concept of industrial maintenance covers several essential maintenance categories, all of which are of great importance. These include maintenance of equipment and materials, of buildings with paints, repair services, maintenance of exteriors, electrical maintenance, fire prevention, and floor cleaning. Industrial maintenance has several advantages that impact on the manufacturing system. First, it reduces the probability of incidents associated with breakdowns and increased safety. On the other hand, it increases the efficiency of the processes, improving the quality of the production and saves unnecessary costs. Finally, it promotes a series of good practices that have a positive impact on operation. For example, maintaining updated documentation specific to each piece of equipment, drawing up maintenance plans, etc. In literature, we can find different nomenclature and group of maintenance management strategies. Surto et al. Consider the following classification for the maintenance procedure: run to failure, preventive maintenance, and predictive maintenance. The first of them, room to failure, also called corrective or reactive maintenance, is pretty simple. Fix things when they break. Since repairs are not planned, it's a good method to employ for equipment that is not essential for operation or that has a low cost. Things, any element that is rarely used or duplicate the function or other equipment. Regarding preventive maintenance, also known as proactive maintenance, this method involves periodically taking assets offline and inspecting for repairing them at predetermined intervals, usually time or event-based trigger. This is the kind of maintenance that we do, for example, with our vehicles. Yearly, we do a revision of the car in order to improve to check if everything is okay. This is essentially preventive maintenance. Finally, predictive maintenance aim to predict failure before they happen, so maintenance can occur at just the right time. Predictive maintenance uses data from matching sensor and smart technology to alert the maintenance team when a piece of equipment is at risk of failing. For example, a sensor may measure vibration of the pieces to alert the maintenance team that a piece of equipment is in risk of failing, at which point it will be taken offline, inspected, and repaired accordingly. The big advantage of this maintenance is that the durability of the element is bigger, hopefully, because the idea is extending at the maximum the functioning of the machinery, but the inconvenience is that you need to collect the information and you need to process too. So as we, sorry, I forgot to say that the treatment of data that we collect in predictive maintenance system is used in a data science process to extract predictive models that are which effectively advise about the possibility of broken up or the necessity of replacing the piece itself. I would say previously, data science is in the heart of predictive maintenance because it provides the knowledge needed to make decisions related to the maintenance actions. In this slide, we can see two of the more common definitions of data science. As can be seen, the main objective of data science is extracting novel and useful knowledge from data. To do that, it gathers information related to the problem to study, the more the better, and applies different techniques based on data visualization, statistics, machine learning, and data mining to extract this new, hopefully actionable knowledge. The following slide shows the different phases that comprise the data science life cycle. As we can see, the first phase is the understanding of the business, that is, the problem object of the study. For example, in predictive maintenance systems, it's important to know the industrial process or the machinery to maintain its principal elements and the failure which can make the system fall down. Once we have a good understanding of the problem, The next step, labeled as data discovery, is the gathering of information. In some cases, this information is available from different data sources, while in other cases, the information is collected ad hoc. In our case, this information usually proceeds from sensor system installed in different elements of the industrial process or the machinery of a study. This information can present potential defects like missing values or liar and other problems that difficult is analyzed. The next phase of the process, data wrangling, is focused on solving the above problems, preparing the information so that it can be passed on to the knowledge discovery algorithms. This algorithm produces models of patterns from the input data, and the next two phases of the process consist on testing this model and evaluating them in order to extract this actionable knowledge of interest. Once the model has been found useful, we can deploy a solution to our problem based on this data. For example, in predictive maintenance, it will be the implementation of a policy related to one or several failure models based on different sensor readings stored in the system. Finally, the data science process is not static. That is, this process can be refined and optimized with successive cycles. Although all phases of the data science life cycle are important, the modeling phase, predictive modeling in the former slide, can be considered the most important one, and it is responsible for obtaining new knowledge, models, or patterns from data. This task, also known as data mining, performs different types of tasks, depending on the type of data available and the type of result to be obtained from it. This slide shows a taxonomy of the principal data mining tasks. At a fifth level, we can differentiate between tasks that produce models that look to the past and data-generated models that look to the future. Regarding to the first group of tasks, we can consider descriptive tasks, where the objective is generating artifacts to describe some feature of data, for example, groups, summaries, or even patterns represented as rules, and diagnostic tasks, where the idea is generating models to categorize data, for example, rules to explain a failure mode in a system. In the second group of tasks, we can consider predictive modeling, which goal is to generate artifacts that predict the value of a magnitude, phenomenon, or process using the information taken previously. Examples of these are classification, where the output belongs to one or several possible categories, and regression, where the output is continuous. On the other hand, in prescriptive modeling, the final aim is generating devices that suggest decision options to take advantage of the result of descriptive and predictive analytics. Typical examples of this kind of model are recommender system, although there are multiple examples of this task. Predictive maintenance research has attracted a great deal of interest from the scientific community in recent years. In fact, the number of publications of the subject has grown exponentially in the last years. In fact, this slide is the result of a search of the term predictive maintenance in the Scopus database and represent the number of papers in journal and in conference that contain this topic in the title or in the abstract. So as you can see, the number of publications has grown significantly. In this section, we will make a brief description of some of the most interesting publications that can be found on the subject. We have tried to select a sample of very recent applications and have grouped them based on the following fields: maintenance of critical components in industrial plants, quality control in manufacturing of electrical components, maintenance of turbofan engines, maintenance of railway networks, and monitoring of functional conditions in vehicles. The first group of applications comprise applications whose objective is to carry out predictive maintenance on critical components of industrial installations which are usually subject to great stress in terms of pressure, temperature, or friction. An example of this kind of component is in rotary motors. This example corresponds to the stainless steel industry. Specifically, it focuses on the machinery involved in the production of high-quality steel sheets, that is, the hot rolling process, and specifically on predicting the degradation on the drums within the heating coilers of steel mills. These are parts with inexpensive replacement that work under severe mechanical and thermal stress. This slide shows a picture of the piece new and after a time very deteriorated and when it needs replacement. To build the predictive model, which is based on a Bayesian filter, the system takes sensor information from the hot rolling processes carried out in the factory, summarize them, and combine with the knowledge of an expert. That is, this is a supervised problem, and the level of the different patterns is set by an expert in the topic that says if the piece has to be replaced or not. The predictive model was fitted and evaluated with real data from about 118,000 processes. You can see the reference in the footnote of the slide, as well as in the rest in the remaining slide that we are going to discuss. Sorry. I have lost a slide, sorry. The second group of application is related to the maintenance of manufacturing elements that affect the quality of electronic components. In this case, visual inspection of the machinery used is practically impossible due to the small scale of the components. For this reason, the use of predictive maintenance techniques based on the analysis of logistic and process variables gathered during the production process will allow the identification of the footprint of this degradation in the data. This first example belonging to the semiconductor manufacturing fabrication consists on the use of an ensemble of classifier using supervector matching as base classifier. The objective was detecting faults in an important operation in the context of semiconductor manufacturing, the replacement of tungsten filament used in ion implantation. This example used 31 variables of the implantation tool, and the obtained result, which accuracies over 98%, demonstrated the effectiveness of the methodology. This other example In this other example, the author introduced Bayesian-based methodology to learn and associate failure signature with potential failure occurrence. In this approach, event-driven maintenance data are used as symptoms which are aggregated on discretized intervals. The failure probabilities as predicted by the Bayesian networks are plotted as temporal evolution. This is further exploited to extract either rules or patterns as failure signature and critical regions. These are then used to monitor and predict the potential failure occurrence. The proposed methodology was tested on data collected for a real manufacturer of semiconductor, and the results were really promising. The third group of applications we are selected is related to the maintenance of turbofan engines. The importance of this topic is clear, given the aircraft are an essential instrument in both the transport of goods and people, and that the cost of breakdown in them will be catastrophic. Due to this and the existence of public data set to monitor the degradation of wind turbines, this area has attracted great attention in predictive maintenance. In this first article of Matthew et al., the author compares several machine learning algorithms in terms of performance in the task of predicting the time it takes for a turbine to fail. Data were taken for a public repository of NASA and contains data from 21 sensors that measure different degradation indicators in 100 turbofan engines. The second article shows a different approach to solve the same problem. The author in this paper used a long short-term memory neural network that you know. There are neural networks specifically designed to learn sequence of data. So are specifically well indicated to learn problems like this to predict an event that will occur in the future. The result that in this slide, we can show the coincidence between predicted values and real data and real values, and to give additional information, the numerical result reported in the paper improve the result of the former paper I described, that include methods at supervector machine, k-nearest neighbors, and other classical machine learning methods. Another example of predictive maintenance is the maintenance of railways networks. This form of transport is growing very rapidly, having the steady progress growth rate is plus 1.5% according to Eurostat. As the railway network are growing very fast and the use is growing a lot, the demand of availability, improved service quality, and reliable infrastructure are more critical. In this case, it's clear that a good maintenance, a good predictive maintenance is necessary for this environment, for these problems. In this first article, author proposed the use of principal component analysis as a method for preprocessing input information to generate new feature that works well together with a supervector machine to predict defects in tracks. As you know, principal component analysis are a method to feature selection and feature synthesis. So the idea is reduce the dimensionality of the problem before passing the information to the supervector machine. Conventional method using input variables use input variable called track quality indices that was obtained combining using different expression applied over the measures that are taken from the railway. This is the difference with this approach with the classical approach. In the classical approaches, the authors, the researcher take the information from the railway and obtain this measure with a mathematical formula and use this as an input to a supervector machine, and this author apply over all the data principal component analysis, obtain new components and use this component as new variable to use in the supervector machine. The result of this approach was much reliable than the original one. In the second example, author developed predictive model that utilizes data from a railway agent. Sorry? Okay, I don't know if I can see anybody. So, okay. Okay, I'm going to continue. I think everything is fine. The last group of applications deals with predictive maintenance in vehicles, cars, and trucks. What happened? As well as I said, the last group of applications deals with predictive maintenance in vehicles. This application has grown recently due to the availability of data to the advance of connected cars and over-the-air technologies. This availability yields a huge opportunity for predictive maintenance to create new business opportunity and a better customer experience, but also for making critical improvement in public services that work with a fleet of vehicles, such as the army or the cleaning services of the cities. I think we are short of time, so I'm going to try to jump these examples. And I'm going to show this last example. I think is the most interesting. This example introduced a fleet maintenance system called eTalk that uses Internet of Things technology and cloud computing to monitor vehicle health and report any anomalies along with information about the nearest maintenance center. Different sensors are attached to the vehicle for monitoring the vehicle health. Data from sensors are received on the information data from sensors are received on the driver's smartphone through a microcontroller, and after processing, useful information is displayed to the driver's mobile screen. The same information is uploaded to a cloud server, where a history of the system is maintained and analyzed for predictive maintenance. The advantages of this system are that it's able to monitor real-time vehicle health statistics, predict fleet health and maintenance, improve vehicle diagnosis, and perform automatic reporting, thus increasing the usable life of the vehicle, fleet productivity and performance. I'm going with the last part of the presentation, introducing the ManPredict project. ManPredict is the acronym of Mantenimiento Predictivo de Plataformas Terrestres. This is a research and technological development project in the field of predictive maintenance of land platforms of the Army. It was selected as one of the 10 research and development projects of interest for the Spanish Ministry of Defense to be included in a program called Coincidente, that is cooperation program in scientific research and development of strategic technologies. The team of the project is made up of researchers from the Cádiz Research Laboratory and experts from the Land Army, specifically experts on the vehicle park of the Land Army. The main objective of ManPredict project is the development of a computing system to give support to the predictive maintenance of several land platforms, specifically tracks of the Spanish Land Army. To build this system, we will use sensor information originated in the different vehicles, as well as historical information available in several databases of the Spanish Army. This system should predict potential failures and support the maintenance policy of the Army vehicle park. This slide shows the architecture of the ManPredict system. This architecture gives support to several operation modes. In edition mode, experts can build predictive models from data, performing the typical data science operation that we showed previously. That is, data preprocessing, data modeling, and model evaluation. Once the model is generated and positively evaluated, it can be stored for future use. In prediction mode, users can use the previously stored models to make predictions about potential failures in the tracks. Once the user inputs the identifier of the track, the system automatically extracts information about it and provides the probability for each of the failure modes defined in the project. Finally, in visualization mode, user can visualize the evolution of the different variables registered for a given platform, for a given track, providing alerts in the case there are anomalous values for any of them. To perform all of these operations, ManPredict includes two information subsystems. The first one, ManPredict Data, is a huge database that stores all the information necessary to build predictive and prescriptive models. And the second, called ManPredict Models, is a database that can be used in prediction mode to select the model to use in predictions and also support experimentation to statistically compare the predictive models. This slide shows in detail the data source involved in the ManPredict project. Each monitor track contains an onboard computer accessible towards a CAN bus. CAN is the name of the bus that communicates the onboard computer with the standard computer. In order to get the communication, the information online, we need a device that connects this CAN bus and communicate it with our servers. the left part of the slide shows that such device. This is a commercial device that connects to the CAN bus and transfer the information via Wi-Fi or different connecting ways to a computer, to our server that contain the information of all the devices. The information sent by every monitor device, by every track of the Army, is stored in a data lake in the man-predict data. That is a data lake, a big data architecture specifically designed to store huge amount of raw data. And beside the sensor information, our system takes information from the Army Logistic Command Database. SIGLE, ITB, and HALTES are three databases of the Army that contain information about the technical inspection of vehicles, the state of the revision, the inventory of the pieces, of the replacement of pieces, and from this information we can also extract valuable knowledge related to the probability of failure in the track. About the state of the project started at the end of 2019 and last 2 years. By now, we have selected the best device to transfer data from the platform. You have seen the device. And we have identified the main failure model by expert of the Army. So we have to develop one predictive model for each failure modes defined by the Army experts. The devices will be installed on 70 tracks, and the data generator will start in October of this year. From this time, we will start collecting data and generating the first predictive models, and our plans are having the first result at the end of this year, once we have a significant amount of information to prepare this predictive model and check the result of them. From September, we will continue with the data collection and STEM model building from the data. To finish the presentation, I will say that in this presentation, I introduced the predictive maintenance as an emerging discipline in the context of Industry 4.0. Its main characteristic is the exploitation of huge amount of data generated by sensors, industrial Internet of Things, to obtain new knowledge that helps to carry out the maintenance of the installation in a more efficient or automated way. In this process, data science plays a crucial role because the model has to be made analyzing the data generated by the sensors. And also we have tried to introduce some interesting cases of study to show that predictive maintenance is still a young research topic. Most of the publications I have shown are from 2015 to 2020, so very recent publication. And it showed that it is a young research topic that offers plenty of opportunities to people interested in industrial research and in the application of data science to real-world problems. So I think I have last the time estimated. Thank you for your attention.
Thank you, Professor Sebastian Ventura Soto. You are talking about a very promising line of research here. Indeed, I have a short question. Perception, I speak about non-precise and noisy sensors is very decisive in the predictive maintenance process, such as cameras or others.
Yeah.
After data acquisition, how to make this maintenance process independent of perception?
Pardon?
I speak about no precise and noisy sensors. Perception in the process of predictive maintenance.
There are examples of the use of cameras and the use of artificial vision in order to check the faults in pieces. So there are multiple examples of the use of this. The question is that the more recent, because you know, these are like now is the time of the industry 4.0, and it's down to using plenty of sensor, and people try to publish applications that use all this information, but it's true that several problems function very well only with cameras or only with sensor. The problem with cameras, you know, is that it's a source of information dedicated, at least in some cases, because it has a lot of problem with illumination, position of the camera. So in a static place where for example, detecting the faults in a piece, if the piece is every time in the same place and the condition where you take the image is exactly the same, is a good way to use a camera, but in other cases it's very complicated. I remember last week
we know actually nowadays that the concept and emerging technology called digital twin take digital twin to take a main place in the smart industry. Okay.
Yeah.
Do you already use this technology, and which one? The driven or model driven one?
This is a slightly different concept. In a digital twin is more related to the simulation of the whole industrial process, and it can be used to make predictive maintenance, because you are taking information from sensors too, and you are emulating the behavior of the whole system. The ideas are similar, but slightly different, because you if you are able to do a digital twin, that is a very complicated task, you can also optimize processes. You can do a lot of different things that are not requisite in predictive maintenance. The only objective on predictive maintenance is optimize the maintenance of the different elements of the industry or of the machine that you want to maintain.
Okay, thank you.
Okay, are there any other question?
Yeah, maybe I have a question for Sebastian. Thank you for this presentation, Sebastian. I have just one question, about, the quality of the results. For example, I am, for example, in engineer school about aeronautics. Sometimes, to do this predictive maintenance for airplane or for critical system, like And then I think the issue of the quality of the result has to be addressed.
The publications show in the aircraft industry there are a lot of results because there are data published by the NASA.
Yeah.
So researchers are working about the public data set published by NASA, and they are getting very good results in terms of accuracy, about 90%, 95%. The results are good.
Okay.
A different thing is that they apply this model on real planes.
Okay.
I am not sure about this.
Okay, yeah. Okay, thank you.
Okay, are there other questions?
If
Yeah.
possible.
Okay.
I just want to ask Mr. Sebastian about the fault tolerance. Is there any mechanism that can be added to your approach so it can be tolerate some rates of faults?
Can you repeat the question? I didn't hear you well.
Okay.
Yeah.
I just was asking about the fault tolerance. Is your model?
Yeah.
Okay. Thank you. Thank you a lot for your presentation. It was very, very, very interesting. Thank you a lot.
The tolerance depends on the specific example, and I guess in our case, for example, the contract that we have signed with the Army established that we have to detect 20 different failure models. Each failure is related to different parts of the track. About, imagine, for example, brakes, the engine. We are going to categorize this failure, and we are going to give a different tolerance in order to the critical of this failure. It's not the same. For example, if if a light is going to be broken, that if the brakes are going to be broken, or if the oil is very hot and the engine is going to break down. So the severity of the failure, the severity of the error is modulated by the severity of the error condition, the importance of the model, and the importance of evaluating the model in terms of not allowing false negatives. In this case, for example, if the problem is very important, if the failure is very critical, we cannot allow a false negative, because the probability is that we predict that there are no problem with the engine, for example, and the engine broke. So in this case, we have to be more conservative. And in other failures that are less important, we can be less conservative and allow that the model has false positives and false negative, because it doesn't matter if we say that the lights are okay or not. You know, I'm not an expert in vehicle, I have to say. I am learning in the project. The project started in January, practically, because we signed the agreement in December, but I am having the meeting with the expert of the Army, and I am learning a lot of things about vehicles, about the temperature of oil, the different element that the onboard computer takes. The onboard computer of these tracks takes about 100 of variables of different parts of the engine. And they are able to track values every 1,000 data per second of each variable. So it's a lot of information. We are learning which information is the most important in each different failure.
Okay, thank you. Thank you for
I hope the project was successful, and I can give you a speech only describing the project and the result that we are getting.